Module 4, Introduction, Lecture A, Ranges and Enumerate. By the end of this lecture, you will be able to use range to generate integer sequences with different start, stop, and step values. Apply enumerate to iterate over sequences while accessing both index and value cleanly. And refactor manual index-based loops into versions that use range and enumerate idiomatically. Understanding range objects. Range as immutable sequence. A range can be thought of as a sequence that represents a series of integers without actually listing each one. It behaves like other sequences because it has a length and you can access its elements. However, it is fixed once created, so you cannot add, remove, or change any values. Its contents are completely determined by its start, stop, and step values, which stay the same for its entire lifetime. In Python, the range function creates an immutable sequence, which means that once it is defined, it cannot be changed. This immutability ensures the sequence stays consistent throughout your program and removes the need to track updates or side effects. When you use a range to represent things like days in a month or seats in a theater, you can rely on those values not being altered by other parts of your code. This stability is especially important in larger programs, where many components might share the same range and accidental changes could cause errors elsewhere. You can think of the range function as an unchanging sequence, which supports a more declarative style of programming. Instead of building and updating a list of numbers step by step, you simply describe the pattern you need, and range represents that pattern in a fixed way. By treating it as a stable, read-only sequence, you can focus on how you iterate over the values, confident that the underlying sequence will not change during your program. Python code. Range as immutable sequence. A range in Python behaves like an immutable sequence of integers. You can use it to get the length of the sequence, access elements by index, and iterate over its values in order. However, you cannot change any of its elements, and any attempt to assign a new value to a position in the range will result in a clear error. This shows that range provides sequence-like behavior while remaining fixed and unmodifiable. We create a range object to represent seat numbers in a small theater, starting at 1 and going up to, but not including, 11. This produces the sequence of seat numbers from 1 through 10. We then print the range object to display its representation and confirm the sequence it covers. To work with a range of seat numbers, we can first use a length function on the range to find out how many seats there are in total. We can then access the first seat by using index 0, just as we would with other sequences. This shows that a range behaves like a sequence, supporting both length and indexing operations to retrieve specific elements. We begin by printing a short message to explain that we are about to go through the seats in order. Then we use a for loop to move through each value in the range of seat numbers. For every seat number in this range, we print it out. This shows how a range can generate a predictable, ordered sequence of numbers that we can reliably use for iteration. This example shows that range objects in Python are immutable. The code attempts to change the first element of a range to 99 inside a try block. Because range objects cannot be modified after they are created, this assignment causes a type error. The except block catches this error and prints a message explaining that the change failed and identifying the error type. This demonstrates that you cannot alter the contents of a range once it has been defined. This script shows that a range object in Python acts like an immutable sequence of integers. It creates a range for seat numbers from 1 to 10 and demonstrates that you can print it, find its length, and access elements by index, just like other sequences. Iterating over the range produces an ordered list of seat numbers, confirming its predictable behavior. When the script tries to change one of the values, it raises a type error, illustrating that range objects cannot be modified once created, unlike lists. Start, stop, step, basics. A range is a counting pattern defined by a start value, a stop value, and a step. You begin at the start, then repeatedly add the step, and you stop once you reach or would go past the stop value. The stop value acts as a boundary and is not included in the sequence. This consistent rule of an inclusive start and exclusive stop makes it easier to understand and predict how any range will behave, even in more complex cases. A range is defined by 3 parts: start, stop, and step. The start value is where the sequence begins, and if you do not give one, it begins at 0. The stop value marks where the sequence ends, but that boundary itself is not included, so the last number is just before it. The step value sets the interval between numbers and can be positive or negative, which lets you create sequences of consecutive values or ones that skip over values. By adjusting these 3 components, you can shape the sequence to match the needs of your specific task. Negative step values are used to create sequences that move backwards. To use a negative step correctly, the starting value must be greater than the stopping boundary, so the sequence can decrease by the step size until it approaches that boundary. For example, a countdown timer might start at a positive number and decrease toward 0, or a review of historical records might start from the current year and step back 1 year at a time. In all cases, the boundary value itself is not included in the sequence. Python code: start, stop, step basics. Explain how the start, stop, and step values define integer counting sequences, making it clear how they control where counting begins, where it ends, and how much it changes each time. Compare forward ranges that count up and backward ranges that count down using simple, everyday counting examples so the difference is easy to hear. Finally, describe printing each range as a list so that the beginning and end of the sequence are obvious, and the whole set of numbers can be seen as a complete unit. In this example, we rely on Python's default behavior where a range without a specified start begins at 0. We set the stop value to 5, which acts as an exclusive upper limit, so the sequence includes 0 through 4, but not 5. The step is 1, so we count every integer in that interval. We then convert this range into a list and print it, clearly showing the numbers from 0 to 4. We set the starting floor to 2, meaning the second floor above ground, and we stop just before 12, so the 12th floor is not included. We choose a step of 3, so we count every third floor and skip the ones in between. Using these start, stop, and step values in the range function produces a sequence that begins at 2, increases by 3 each time, and ends before 12. When we print this sequence, it shows the visited floors as 2, 5, 8, and 11. We create a countdown by starting at 10 seconds and setting 0 as the stopping point, which is not included. The step size is -2, so the time decreases by 2 seconds at each step. This produces a list that goes backward from 10 down to 2, skipping 0. When we print the list, the countdown sequence is 10, 8, 6, 4, and 2. This script shows how Python's range function can generate different integer sequences by changing the start, stop, and step values. It first creates a simple forward sequence from 0 up to, but not including, 5. Then, it demonstrates a custom forward sequence that starts at 2, increases by 3 each time, and stops before 12. Finally, it produces a backward countdown that starts at 10, decreases by 2 each step, and stops before 0. Each of these sequences is displayed as a list, so the chosen boundaries and step sizes are easy to see. Memory efficiency of range. Ranges are efficient because they represent large sequences of numbers without storing every value in memory. Instead, they only keep track of the start, stop, and step, but still let you iterate and access positions like a regular sequence. As a result, the memory used is the same whether the range covers 10 numbers or 10 million. This compact design is especially important when working with large numeric intervals, such as iterating over many days, because it avoids overloading memory. When working with loops, it is more memory efficient to generate each value only when you need it, instead of storing all values at once. In tasks like simulating population growth or processing high-resolution images, keeping every index in a list can waste a lot of memory. Using a range object lets the program produce each index on demand without holding the entire sequence in memory. This approach helps your code handle larger datasets and is especially important in areas like data analysis and scientific computing. When you pass a range to a function, you are giving it a small, efficient object that describes a sequence, not a large container holding every value. This makes ranges easy to share across your code, store temporarily, or create on the fly from user input. For instance, a scheduling tool might represent time slots as a range, and a game engine might use a range for levels or grid positions. Because ranges only describe the sequence, instead of storing all its elements, they help keep your program efficient and responsive, even as the sequence grows large. Python code, memory efficiency of range. This section explains that the range construct uses very little memory, even when representing huge sequences of integers. It contrasts this with lists, which store every integer explicitly and therefore consume much more memory for the same number of elements. By comparing their memory usage for similar integer counts, you can see why range is a better choice for large loops and index sequences. The main goal is to help you recognize when to prefer range over list to keep your programs more memory efficient. We begin by importing the system module in Python so we can inspect how much memory different objects use. This module provides a function that returns the size of an object in memory. By calling this function, we can compare the memory consumption of various data structures. This is especially helpful when working with large sequences where memory efficiency becomes important. We start by turning a range of 10 integers into a list, which explicitly stores the numbers from 0 to 9 in memory. We then create a range object with the same 10 integers. Unlike the list, the range does not store all the numbers at once, but generates each value only when needed. This difference lets us compare how much memory a list uses versus a range of the same size, highlighting that the range is more memory efficient. We first check how much memory is used by a small list that holds 10 integers, which shows the memory cost of storing a short sequence as a list. Then we check the memory used by a range that represents the same 10 integers. Comparing these two results demonstrates that a range is more memory efficient than a list for representing the same sequence of numbers. We first build a large list of 1 million integers, from 0 up to just under 1 million, by generating the sequence and converting it into a list stored fully in memory. Then we create a large range object that represents the same sequence of 1 million integers. The key difference is that the list holds every number at once, while the range object does not store all values in memory. Instead, it produces each number only when needed, which makes the range approach much more memory efficient for very large sequences. We use the getSizeOf function from the system module to measure how much memory is used by a list that stores 1 million integers. Then we measure the memory used by a range that represents the same sequence of integers. Comparing these two results shows that the range object uses far less memory than the list. This demonstrates that ranges are much more memory efficient than lists for representing large sequences of numbers. We compare the memory usage of a large list and a large range by using a system function that reports how many bytes each one takes. By dividing the memory size of the list by the memory size of the range, we get a ratio that shows how many times more memory the list uses. This calculation demonstrates that a range is much more memory efficient than a list when representing large sequences. The code finishes by printing how many times more memory the large list uses compared to the large range. It does this by dividing their memory sizes and rounding the result to 1 decimal place. This clearly shows that using a range for large sequences is much more memory efficient than using a list. This script shows that using a range object in Python is much more memory efficient than using a list. Even for just 10 integers, a list takes more memory than a range of the same size, and this gap becomes dramatic with larger sequences. For 1 million integers, the list uses far more memory than the corresponding range. By calculating and displaying the ratio of their memory usage, the script highlights that range is a better choice than a list for large loops or index sequences when conserving memory is important. Enumerate basics. Intro to Enumerate. When you loop through a list, string, or other sequence, you often need both the item and its position. A common beginner approach is to keep a separate counter or loop over index values, but this makes the code longer and less readable. The enumerate function solves this by automatically giving you each index together with its corresponding value. This way, you do not have to manage a counter yourself or look up each element by its position. You can think of the enumerate function as a helper that moves through a sequence and gives you both the position and the item at each step. It automatically keeps track of the count, so you do not need to manage indexes yourself. This makes loops easier to read because you are clearly working with both the index and the value. For example, when processing survey responses, Enumerate lets you access each response along with its position in the dataset, similar to a row number in a spreadsheet without any extra work. Using an enumerate-style tool is most helpful when the index itself is meaningful, not just a counter. For example, you might need to state a student's position in a class list, show track numbers with song titles, or track the time step of sensor readings in data analysis. In these cases, you care about both the item and its position. Enumerate lets you write loops that keep the index and value together in a clear, compact way that matches how you naturally think about ordered data. Python code. Intro to Enumerate. This section explains how to use the enumerate feature with a simple list. It shows that enumerate gives you both the index and the value at the same time as you loop through the list. It also contrasts this with manually tracking an index, highlighting that using enumerate leads to cleaner, more readable looping code. We begin with a list of 4 fruit names: apples, bananas, cherries, and dates. Then we create a separate counter variable and set it to 0. This counter will be used to keep track of the position of each fruit as we go through the list. In other words, we are manually tracking the index of each item in a way that imitates what the enumerate function would normally do for us automatically. We begin by indicating that we are using manual index tracking, then loop through each element in the list of items. During each pass through the loop, we announce the current item number stored in the manual index variable, along with the item's value. After reporting this information, we increase the manual index by 1 so it correctly reflects the position of the next item in the sequence. We use a short message to introduce that we are demonstrating the enumerate function in a loop. Then, we apply this function to a list of items so that each loop iteration gives us both the index and the item. Inside the loop, we print the current index together with its item. This method is more concise and readable than manually keeping track of the index, because the function automatically handles the numbering for us. This script compares 2 ways to loop through a list of fruits and shows why using the enumerate function is better. The first loop manually tracks the index while printing each fruit, which is more cumbersome and easier to get wrong. The second loop uses enumerate to automatically provide both the index and the fruit, making the code cleaner and more readable. Both loops produce the same output, but the version that uses enumerate is more concise and is generally preferred in Python for this kind of task. Custom Enumerate Start. When using the Enumerate feature, you can choose any starting index instead of being limited to 0. This is helpful in situations where counting naturally begins at 1 or at another meaningful number, such as numbering survey questions or chapters. By setting a custom starting index, you keep the numbering familiar and human-friendly while still getting both the index and the value during each loop iteration. Using a custom starting index in an enumeration is not just cosmetic. It helps avoid off-by-one errors and makes code easier to understand. When your index matches real-world labels, such as starting weekly sales at week 27, you no longer need to translate between zero-based counting and actual week numbers. This direct alignment simplifies loop logic, reduces mistakes, and makes it clear to anyone reading the code that the index represents meaningful labels like week or seat numbers, not just list positions. Using a custom starting index with an enumeration tool is useful when you are working with partial data or continuing a process from where it left off. For example, if one batch of log entries covers 1 through 1000, you can start the next batch at 1001, so the numbering stays consistent. The same idea applies when numbering exam questions across sections or labeling video frames in chunks. By choosing the right starting index, your loop automatically matches the larger data context, keeping outputs aligned without extra calculations. Python code, custom enumerate start. Use the enumerate function with a custom starting index when you want human-friendly numbering in a loop. For example, survey questions are usually labeled starting from 1, not 0, so adjusting the start value makes the labels match what people expect. Comparing the default zero-based behavior with a custom start value helps clarify how the loop index changes and why setting the start can make the code's behavior clearer. We create a list of survey questions, each stored as a short text about daily activities such as miles walked, cups of coffee consumed, and hours slept. This list lets us loop through the questions one by one. It also sets up an example of how to use the enumerate function with different starting index values to label each question in a flexible way. We demonstrate the default behavior of the enumerate function, which starts counting from 0. As we loop over a list of questions using this function, we get both the position and the question text for each item. The position value begins at 0 and increases by 1 for each question. Inside the loop, we print a message that shows the current position alongside its question, clearly illustrating how zero-based indexing works in this context. The code adds a blank line between two sections of output to clearly separate them. This visual break makes it easier to see where the default enumerate example ends and the custom starting value example begins. As a result, viewers can more easily compare the two demonstrations without mixing up their results. We begin by printing a message to explain that we are using a custom starting index for our loop. Then we call the enumeration tool on the list of questions and set it to start counting at 1 instead of the default 0. In each loop, we get both the question number and the question text. We print them together in a formatted line so that the questions are labeled starting from 1, which is more natural and clear for most users. This script shows how Python's Enumerate feature can use a custom starting index. It first demonstrates the default behavior, where counting begins at 0, and each survey question is paired with its index. It then switches to a more human-friendly style by starting the count at 1, which matches common numbering in everyday use. This makes the list of survey questions clearer to read and understand. Overall, the script highlights how flexible the Enumerate feature is for adjusting starting points to fit different presentation needs. Index value unpacking. When you use the Enumerate feature in a loop, you work with two values at the same time, the current position and the element at that position. This is called index value unpacking because the pair is split into two separate variables as you iterate. The loop header performs this unpacking for you, so you do not have to separate them manually. This makes the code clearer and shows that you are intentionally using both the positions and the elements together. Using index and value together in a loop is helpful when the position of each element matters. It lets you work with both the item and its number in the sequence at the same time, such as labeling survey responses by their response number while showing the actual comment. The same idea applies to data like daily temperatures, where the index can stand for the day and the value for the temperature. This makes it easy to add logic based on position, like treating the first day differently or checking when values pass a certain limit, without writing extra code to track where you are in the sequence. Using index and value unpacking with the Enumerate tool lets you avoid errors that come from managing indices by hand. Instead of keeping a separate counter and risking off by one mistakes, you let Enumerate handle the counting and unpack its results into two variables. This keeps your loop focused on the real task, such as annotating logs, tagging images, or matching students to grades. As you use it more, this pattern becomes a natural choice whenever you need both the position and the value from a sequence, making your code safer and clearer. Python code, index value unpacking. Use a simple list of survey responses to demonstrate how unpacking both the index and the value from an Enumerate-style loop makes the code clearer and safer. By giving meaningful names to the index and the response value, it becomes obvious what each part of the loop represents. This approach reduces the risk of off-by-one errors and confusion that can occur when manually managing index variables. Comparing the unpacked Enumerate loop with a traditional loop that accesses list elements by index highlights how much readability and reliability improve when both the position and the value are handled together. We begin by creating a list called responses that holds 3 different survey answers, each stored as a separate text entry. This list serves as our sample data. We will later use it to show how to access each individual response and display it together with its position in the list. This example shows a manual way to track positions while looping through a list of responses. We start by announcing that we will use manual index access, then set a counter to 0 to represent the current position. As we loop over each response, we print the response number by adding 1 to the counter, along with the response text. After each print, we increase the counter by 1 to move to the next position. This method works, but keeping a separate counter can be more error-prone and less readable than other available approaches. We use a print statement to introduce an example that demonstrates using the Enumerate function with index value unpacking. In the loop that follows, we iterate over the list of responses, while Enumerate provides both the index and the response itself. We set the starting index to 1, so the position count begins at 1 instead of 0. Inside the loop, we print each response together with its position, clearly showing which response matches which index. This method improves readability and helps avoid mistakes compared to tracking the index manually. This script compares two lays to loop through a list of survey responses. First, it uses a manual counter to track each response's position, which works but can be harder to read and more prone to mistakes. Then it uses Python's Enumerate function, which automatically provides both the index and the response starting from 1. Both methods produce the same output, but the version that uses Enumerate is cleaner, easier to read, and shows the advantage of using built-in tools for common tasks. Refactoring index loops, replacing while with range. When you first write loops, you might use a while loop with a counter that you set up, check, update, and increment yourself each time. This works, but it spreads the logic across several steps, which can make the code longer and easier to get wrong. A better option is to use a loop based on a range of integers, which directly represents the sequence you want to iterate over. This approach makes the code clearer and reduces the complexity of managing separate pieces of loop logic. Refactoring a counter-based while loop into a range-based loop means recognizing that the counter simply steps through a predictable sequence of numbers. Instead of manually initializing, checking, and updating the counter, you specify the start, stop, and step values as a range. This makes the loop clearer and more concise, so you can focus on the actual work done at each position, such as checking string formatting or scheduling resources, rather than on the mechanics of managing the counter. Using a range-based loop makes your code safer and easier to manage because the start, stop, and step values are all defined in one place. If you need to change how many times the loop runs, you only adjust the range settings instead of hunting for counter updates inside the loop body. This reduces mistakes, like forgetting to update the counter or changing it incorrectly. Overall, it makes loops clearer to read, understand, and review. Since the sequence of indices is explicit and the language takes care of the repetitive bookkeeping that a while loop would require you to handle yourself. Python code, replacing while with range. Demonstrate how a manual while loop that uses a counter can be rewritten using a range-based loop. Then, compare the outputs of both versions to confirm they behave the same. Emphasize that the range-based version is cleaner and more compact, while preserving the original logic. The main goal is to practice refactoring counter-driven loops into simpler, range-based loops without changing their behavior. We begin by creating a string with the value USA, which will be the focus of our loop. We also set up a counter variable starting at 0 to keep track of our current position in the string. Before running the loop, we print a short message to explain that we are about to show each position in the string, along with the letter found at that position using a while loop. This prepares us to see how the loop moves through the string one character at a time. A while loop can be used to go through a string one character at a time, by running as long as the index is less than the length of the text. On each pass through the loop, you look up the character at the current index and output both the index and that character. After printing, you increase the index by 1, so the loop moves to the next position. In this way, the loop visits every character in the string in order, allowing you to process or display each one sequentially. This line simply prints an empty line to the console. Its purpose is to visually separate the outputs produced by the two different loop styles. By adding this blank space, it becomes easier to see where one loop's results end and the others begin. This helps you compare their outputs more clearly. We begin by printing a short message to explain that we are about to use a range-based loop to go through each position and letter in a string. This introduction highlights that a for loop using a range can perform the same task as a while loop. The key point is that the for loop version is more concise and easier to read while producing the same result. We use a for loop to go through each position in the string by generating index numbers from 0 up to 1 less than the length of the string. For every index, we look up the character stored at that position. We then output both the index and its corresponding character, showing how each position maps to a specific letter. This method is concise, clear, and easier to read than using a manual while loop to do the same task. This script shows two ways to loop through a string in Python. It first uses a while loop to print each character of the word USA along with its position until it reaches the end of the string. Then it rewrites the same logic using a for loop with a range, which produces the same output in a shorter and clearer way. The example illustrates that using a range-based for loop can simplify counter-driven loops and make the code easier to read. Dropping manual counters. Beginner code often uses a separate counter that is set before a loop and manually updated inside it. But this can be wordy and easy to get wrong. Modern practice is to let the loop structure handle counting for you. This allows you to focus on the main task instead of managing the counter. As a result, your code becomes shorter, clearer, and less likely to contain subtle bugs that are hard to find. When you use a counter only to track positions or label iterations, it is better to use more expressive loop constructs. For a fixed number of iterations, rely on a range-based loop so positions are handled automatically. When you need both the index and the value from a list or string, choose a construct that directly provides both instead of doing manual index math. This keeps the loop header clear about how many times it runs and what data you get, while the loop body stays free of counter updates. As a result, the code is easier to read, reason about, and change without breaking the counting logic. When you need both the position and the value of items in a list, such as survey responses or daily temperatures, manually keeping a counter in sync with the data can be error-prone. You have to remember to initialize and update the counter correctly, and it can easily get out of alignment if you skip items or exit the loop early. Using language features that automatically provide both the index and the value avoids these synchronization problems. This makes your loops clearer, safer, and more flexible because the language handles the counting while you focus on processing the items themselves. Python code, dropping manual counters. This lesson explains how to replace manual counters with range-based loops and with loops that automatically provide both the index and the item. It shows how manual counters can drift out of sync when conditions or loop behavior change unexpectedly. By contrasting this fragile manual counting with safer automatic counting tools, it highlights why relying on built-in mechanisms is more robust and less error-prone. We define a list of possible responses, such as yes, no, maybe, and skip, and then set up a separate counter variable starting at 1 to track our position in the loop. As the loop runs, each response is processed in turn, while the manual counter is updated independently. This example is used to show that a manually maintained counter can easily become inaccurate, especially when some responses are skipped or not handled in a straightforward way. It highlights the potential mismatch between the actual loop position and what the manual counter reports. The code checks whether the current response is labeled as skip. If it is, it prints a message saying that this response is being skipped at the current manual counter position. It then increases the manual counter by 1 to move to the next position. Finally, it uses a continue statement to jump to the next loop iteration so that no further processing is done for the skipped response. The code prints a message that shows the current value of a manual counter together with the current response, so you can see which response is being processed. After printing, it increases the counter by 1 to prepare for the next loop iteration. However, this manual increment can become inaccurate if the loop logic changes, such as when some responses are skipped. In that case, the counter may no longer match the actual position in the sequence of responses. We switch to a safer counting method by using an enumeration approach and announce this change to the listener. Inside the loop, enumeration gives us both the index and each response automatically. We start counting at 1 to match typical human numbering. This ensures the index always matches the actual position of each response, even if some are skipped. As a result, the counting stays accurate, consistent, and reliable throughout the process. The code checks whether the current response is the word skip. If it is, it prints a message saying that the response at the current position, identified by its index, is being skipped. After printing this message, it uses a continue statement to jump directly to the next loop iteration. This means no further processing is done for that particular response. This line prints a message that shows the current position of each response in the list, using the automatic numbering provided by the Enumerate function. It confirms that the reported position matches the response being processed. This helps verify that the counting logic is correct and stays accurate even if some responses are skipped. This script shows why manually counting positions in a loop can be unreliable and how using Python's Enumerate function solves the problem. When a manual counter is used to track items in a list, skipping an item still increases the counter, so the recorded position no longer matches the actual processed item. This drift makes the manual count inaccurate and error-prone. By switching to the Enumerate function, the script automatically keeps track of each item's index, so the position always matches the real location in the list, even when some items are skipped. Preventing off by one. Refactoring loops to use range and enumerate helps prevent common off-by-one errors in iterative code. These errors happen when loops run too many or too few times because the starting point, ending point, or step size is set incorrectly. Manually managing index variables requires careful setup, boundary checks, and updates, where even small mistakes can cause elements to be skipped or processed twice. By contrast, using range and enumerate automates much of this index and boundary handling, making it clearer where loops start and stop and improving overall code reliability. When comparing each day's temperature to the previous day, manually managing index values can easily cause mistakes, such as starting at the wrong position or going past the end of the list. Using a range-based loop with clearly defined, valid indices, starting at 1 and stopping at the list's length, helps avoid these off-by-one errors because the end value is not included. Thinking in terms of these half-open intervals becomes a consistent habit that makes many different looping situations safer and more reliable over time. Using the enumerate feature in a loop lets you access both the index and the value at the same time without keeping a separate counter. This avoids mistakes that happen when you forget to update a manual counter or update it incorrectly. As a result, the index always matches the current element, which helps prevent off-by-one errors. Overall, using enumerate makes your loops clearer, safer, and easier to maintain than managing the index yourself. Python code, preventing off-by-one. Manual counters in loops often lead to off-by-one errors, where the index starts or ends at the wrong value. To reduce this risk, it is safer to use language features that generate index ranges for you, such as a range-based loop or a construct that automatically provides both the index and the item. These approaches rely on half-open ranges, which include the start but exclude the end, and they keep the index automatically aligned with the data. As a result, you write less error-prone code and avoid many common boundary mistakes. We use a list of daily temperatures in degrees Fahrenheit to illustrate how off-by-one errors can occur in loops. The list contains 4 values: 70, 72, 69, and 75. By working with this simple set of temperatures, we can focus on how different looping techniques access list elements and how mistakes in index ranges can lead to incorrect results. This example highlights an off-by-one error in a loop that processes a list of temperatures. An index starts at 1 and is used to access the current and previous day's temperatures for comparison. The loop condition allows the index to go up to the length of the list -1, which is incorrect. Because of this, the loop can run one step too far and attempt to access a temperature beyond the valid range of the list, risking an index out of range error on the last iteration. This code prints a formatted message that compares today's temperature with yesterday's. It does this by using the current position in the list to get today's value and the previous position to get yesterday's value. After printing the comparison, it increases the position by 1, so the loop can move on to the next day's temperatures. We use a loop that goes through the list of temperatures, starting at the second item and stopping just before the end of the list, following the common half-open range pattern in Python to avoid off-by-one errors. On each pass, we store the current day's temperature in one variable and the previous day's temperature in another. This makes it easy to compare temperatures from consecutive days throughout the list. This line prints a formatted message that compares today's temperature with yesterday's. It uses the current position in the data to identify the day, then looks up today's and the previous day's values in the temperature list. The result is a clear, readable output that shows how the temperature has changed from one day to the next. We use the Enumerate feature to loop through the temperatures list while automatically keeping track of each position, so we do not need a separate counter. As we iterate, we log that we are checking for cold days, and for each temperature, we get both its index and its value. Inside the loop, we test whether the temperature is below 71 degrees, and if so, we print a message that includes its position in the list and the temperature. This method helps avoid off-by-one errors because Enumerate manages the indexing for us. This material explains how off-by-one errors can happen in loops and how to avoid them in Python. It first shows a faulty loop that runs one step too far and causes an error when accessing a list of temperatures, illustrating the risk of manually managing indices. It then fixes the problem by using a range-based loop, which clearly defines where the loop should start and stop. Finally, it demonstrates using the Enumerate function to iterate over the list while automatically keeping track of positions, making it easier to find and log colder days and reducing the chance of index errors. In this lecture, you learn to use range to generate integer sequences with different start, stop, and step values. Apply Enumerate to iterate over sequences while accessing both index and value cleanly. And refactor manual index-based loops into versions that use range and Enumerate idiomatically. In the next lecture, Lecture B, we will go over zip map filter.
Thank you for your attention. See you all in the next lecture.